We are now beginning Chapter 8, which is all about energy balance calculations. So we've had Chapter 7, we had an introduction, and now we are going to look at more detail in different features of energy balance, such as temperature changes, pressure changes, phase changes, and we're also going to learn in this chapter how to use the psychrometric chart. So for this first lecture, we are going to consider hypothetical process paths, which is often an area that students find particularly challenging. We are also going to talk about an accounting procedure that's called an enthalpy table. And you need to learn how to prepare this table and use it for your energy balance calculations. So this kind of diagram that I drew here gives you the example of a hypothetical process path. And it's not meant to represent anything real. It just shows that if you have, say, a temperature change, if this is your initial point and this is your final point, that the actual enthalpy may not follow this a straight line such as this, where you have a temperature change, and then you have a time change where there's no temperature change, followed by another temperature change. The real path may be something, skewed, but it's okay because since enthalpy is a state variable, we can reorganize it in a way that is convenient for our calculation. We simply need to know H2 minus H1 from the initial to final states, and we need to find ways to calculate delta H with information that we have accessible to us. So this kind of skewed process path would be difficult for us to calculate, but we can probably find delta T's, information about enthalpies with delta T's and that sort of thing. So this also is an example of a process path. Oops, I'm sorry. If here's an example of a path, that you may take if it's a constant pressure process. So we're following a constant pressure here, but it's going through temperature changes, volume changes, and enthalpy changes. So we have to learn how to make that calculation. Here's an example of a enthalpy. This is an enthalpy, a temperature enthalpy diagram. Okay, this is for steam. All right, so this is actually a boiler. Okay, we are going to increase the temperature, and then we are going to increase the enthalpy at constant temperature, and we are going to then raise it to its final superheated state. So this just shows you the actual physical diagram of the relationship between temperature and enthalpy and the process by which we would do the calculation. So the steps on that diagram would be the following: increase in temperature at constant pressure to the saturated liquid line, increase in enthalpy at constant P and T to the saturated vapor line, followed by the increase in enthalpy and temperature at constant P to the final state. So we are able to find these information on our steam tables. In fact, the reality is that we can just do the total delta H, but the steps that go through the different parts of the process can also be found, and you can use that partial information to learn about other features of the process that may not be so clear. So for process paths, we ideally, if all the information is taken from the same source, such as the steam tables, we only need to know H1 and H4 to calculate delta H. But there are times that we may need to find it from different sources. Okay, so the point of this chapter is that we learn how to find or calculate enthalpy changes for different species, across phase barriers, and for different changes in state properties. So we find enthalpy changes, and then we can sum them up to determine the enthalpy change for the complete process or for a process step. So this is a picture here of the enthalpy table that we should start using for accounting. Okay, it's about proper accounting of our enthalpy changes. And it's not that difficult here, okay? So this is the calculation. 40 kilograms per hour of steam at 200 degrees C in 1 bar is used to heat a process stream with a condenser. The steam exits a condenser saturated at 1 bar with 80% of the stream exiting as a liquid. How much heat is added to the process stream in kilowatts? So let's look at the features of the enthalpy table. Okay, so first thing is we need to list here the reference state for each species on our table. In this case, we only have water, and we're going to get all our values from the steam tables. So the reference is water at the triple point. So now this is not 2000 C, it's 200. This should be a superscript degrees C. Okay, so we have water vapor at 200 degrees C, liquid water saturated at 1 bar, and vapor water saturated at 1 bar. Okay, so now what we have to do is this is these are the columns. We have the substance. Okay, and we may have other substances listed on the table here, but here we only have water in the different states that it occurs in our process. Then in the other columns we have the N in, and here it's mass. Okay, this is really an M dot. Mass in kilograms per hour in to the process, and this is going to be the M dot out from and if there's a phase change, you know, some may move around. So M dot in is not necessarily equal to M dot out in each row, but the total M dot in will equal M dot out unless we have a chemical reaction, which is what we're going to be doing in chapter 9. So all of chapter 8, we not have any chemical reactions. Okay, so we need to fill in these values, okay, from our mass balance. We can fill these in. And then we find the enthalpies from, in this case, we find them from the steam tables. In other cases, we may have to calculate them. Okay, so we have, this is going to be the outflow rates and the specific enthalpies for inlet and outlet process. So notice that we're going to have here, we have our N dot is kilograms per hour, and our H hat is kilojoules per kilogram. So we're going to end up with a delta H here. It's our enthalpy is going to be calculated in terms of kilojoules per hour, because we're going to multiply this times this. Okay, and the same on the outlet. And so we sum up. This is the calculation of our enthalpy change. Okay, and then once we have that, we realize that Q dot is Q dot minus W dot is equal to delta H times M dot. Okay, so this would be the entire energy balance that we will use. Okay, and so first we do the mass balance and find all the flow rates. So it may be mass, it may be moles. Then we find or calculate values for each enthalpy. And as we go through this chapter, you're going to learn how to do that for the different species. And then once you have the table completed, you solve for delta H, which is the sum of N dot out, H hat out, minus the sum of N dot in, H hat in. So here we have the table completed that we now, based on the problems, that we had this going in, and coming out we had 80% coming out as a liquid, 20% coming out as a vapor. And these are the enthalpy values that we would find on the steam tables. And when we do the calculation, the sum of M dot out, H hat out is going to be this times this plus this times this. So this times this plus this times this. And then we subtract the inlet, this times this. And from there we were able to calculate the delta H And this is in kilojoules per hour. If we convert hours to seconds, then we have minus 22.3 kilowatts. So what we've seen in this section is that we can map process paths to enable the calculations, and we should assemble the enthalpy information into a table format. Okay, so this is going to be very helpful, especially once we start having chemical reactions. So here is your video quiz, and I'm giving you a lot of information to help you do this calculation. Okay. In a device to produce drinking water, humid air at 32 degrees C, 90% relative humidity, and 1 atmosphere is cooled to 5 degrees C at constant pressure. If the duty on the unit is 2200 kilowatts of heat removed from the humid air, how much water is produced, and what is the volumetric flow rate of air entering the unit? I will point out that this is a simultaneous material and energy balance. Okay, you have to do both material and energy balance to find the flow rates. And once you find the flow rate of water produced, you can calculate the amount of air entering, and then you can use the ideal gas law, okay, to find out the volumetric flow rate. So I'm giving you all this information. Okay, we're going to, as we proceed through the chapter, you're going to see where we find the information. You could find all the steam values already on the steam tables, but I'm going to give them to you here just to facilitate. But since I'm giving them to you, you could check and make sure for yourself that I've got the right values. All right, so you want to find, now what you're going to need to do is find mole fractions of water and dry air. You can do that using Rail's law. Y of H2O times P is equal to P star. And in the case where we have 90% relative humidity, then you're going to use the relative humidity equation. On the outlet, we will have saturated. This is coming out saturated at 5 degrees C. So you can just use the Rail's law for the exit. On the inlet, you need to use the relative humidity information, the calculation. Okay, so here's the suggestions about how to approach this. Determine the mole fractions of water and dry air at the inlet and outlet. Write the number of moles in each box under the n dot columns in terms of a single variable. May I suggest the n dot of humid air entering? N dot of HA entering could be your variable. And then you can multiply the mole fraction of the air times that value and the mole fraction of water times that value. We don't have any liquid water going in, so this is nothing. And you can do the same thing on the outlet. And then you can do the energy balance to find how much liquid is going to be coming out. Okay, good luck.